For most of our history, human technology consisted of our brains, fire, and sharpsticks. While fire and sharpsticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and the control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of data processor in computers, basically a switch that can either block or open way for the information coming through. The information is made up of bits that can be set to either 0 or 1. Combination of several bits are used to represent more complex information. Transistors are combined to create logic gates which can still do very simple stuffs. For example, an AND gate sends an output of 1 if all of its input are 1 and output of 0 otherwise. Combination of logic gate finally forms meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all the basic operations are simpler than first grade math, you can imagine a computer as a group of 7-year-olds really answering simple basic mathematical questions. A large enough bunch of them could basically compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics is making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another. So a switch is passage that can block electrons from moving in one direction. Today, a typical scale for transistor is 14 nanometers, which is 8 times less than that of HIV virus diameter and 500 times smaller than that of red blood cell. As transistors are shrinking to the size of few atoms, electrons may just transfer themselves to other side of blocked passage by the process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable way we are used to. The traditional computer just stopped making sense. We are approaching a real physical barrier to our technological process. To solve this problem, scientists are trying to use the unusual quantum properties to their advantage by building quantum computers. In normal computer, bits are the smallest unit of information. Quantum computer uses qubits, which can be set to one of the two values. A qubit can be any two-level quantum system such as spin and magnetic field, or a single photon. 0 or 1 are this system possible state, like photons horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of these states. It can be in any proportion of both states at once. This is called superposition. But as soon as you test its values, say by sending a photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it is unobserved, the qubit is in superposition of probabilities for 0 and 1, and you can predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power 4 different configurations at a time. That's 16 possible configurations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store a million values in parallel. A really weird and intuitive property qubits have is entanglement, a close connection that makes each of the qubits react to a change in other state instantaneously, no matter how far they are apart. This means when measuring just one entangled qubit, you can deduce the properties of its partner without having to look. Qubit manipulation is a mind bender as well. A normal logic gate gets a simple set of input and produces one definite output. A quantum gate manipulates an input of superposition, rotate probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and then finally measure the outcome, collapsing superposition to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculation that are possible with your setup all done at the same time. A Ultimately, you can only measure one of the results, and it will be only probably be the one you want. So you may have to double check and try again. But cleverly exploiting superposition and entanglement, this can be exponentially more efficient than it would ever be possible on a normal computer. So while quantum computers will probably not replace our home computer in some areas, they are vastly superior. One of them is database searching. To find something in database, a normal computer may have to test every single of its entities. Quantum computer algorithms need only square root of that time, which for large database is huge difference. Most famous use of quantum computer is ruining IT security. Right now, your browsing, email, and banking data are being kept secure by an encryption system in which you give everyone a public key to encode message only you can decode. The problem is that this public key can be used to calculate your secret private key. Luckily, doing necessary maths on a normal computer would take years of trial and error, but a quantum computer with exponential speed could do it in a breeze. Another really exciting new use is simulations. Simulations of quantum world are very intense on resources, and even for bigger structures such as molecules, they often lack accuracy. Quantum simulations could provide new insight into proteins that might revolutionize medicines. Right now, we don't know if quantum computers will be just a specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there is only one way to find out.